Today we'll finish control flow, and I hope to get started on out-of-order execution, but there is an important concept we need to cover in pipelining before we do that, which is exceptions. You may have realized there are issues with exceptions in a pipeline while you're doing your current lab, and we will see some solutions to that problem. I guess this doesn't work anymore. There you go. Okay. Your homework is due today. I hope you're all done. And if you haven't started, you're in trouble for the lab assignment. How many of you haven't started yet? Good. You're shy to raise your hand if you haven't. How many of you have completed the lab? Don't be shy. There are a couple. 3, 4. It's good. Are you doing the extra credit? No? I guess we'll see. Okay. You know the extra credit portion. Well, I guess the first thing is gone, so you cannot get extra credit for early checkoff anymore, but you can still design the fastest design, CPI times clock cycle time. You can minimize that. Okay. Feedback sheet, don't forget this. Will be online today. Is stale because I copied and pasted the slide. This is a copy-paste error. This is already online, this feedback sheet. Please return it by Wednesday. And you can use any means you would like to return it. And you can return it anonymously. We'd like to improve the course. And on that note, there's an important thing coming up next week. March 7th, we'll have the midterm. So I hope you guys are studying. Some ground rules, it's closed book, closed notes, except you can bring a single 8.5 by 11 letter-sized cheat sheet. So you can write in any font you like in that cheat sheet, as long as you can read, I assume. Okay, and if we need to give you some additional sheets, we will give you additional sheets. I don't want you to memorize a lot of things. But we'll have more on the exam later. And we will have a review session on March 5th. Okay, any questions? Okay, let's defer those to Wednesday. Okay, these were the readings for today. I hope you guys have read these. How many of you have read the Smith and Sohi paper? 0? You guys are all busy with labs? Please read it, because that describes how an existing microarchitecture actually works. So it's very informative. Even though it was written in 1995, it covers the fundamentals of out-of-order execution and superscalar execution. And it puts a lot of things together. And I'd like to get your feedback on how difficult of a read it is. I don't think it's very difficult. It's relatively easy. But we haven't covered all the concepts yet. But this is required reading. So there may be questions on the exam related to it. Okay? Fair? All right. There's a calcium seminar this Wednesday also. I don't know if you guys are attending. I think I saw 1 or 2 of you in the last seminar, which was good. This seminar is interesting. It's 4 to 5 p.m. Wednesday again. It's on what happens to DRAM errors. Like you have dynamic random access memory, and when you store a bit, that value can change if a particle hits. Right? That's what they mean by cosmic rays don't strike twice, I assume. And if the bit changes from 1 to 0, how do you handle it at the system level? So these are important issues that computer architects today deal with. What happens, you have a value in your register file, and a cosmic ray hits it, and that value becomes 1 instead of 0. How do you deal with it? Well, maybe you guys can come up with some ways of doing it. A common way of dealing with it is how to detect the error, right? Maybe you store 2 copies of your register and check if they're the same, right? You always write to both copies. And if they're the same, then the hope is that both of them did not change the same way. Right. Or you can store 3 copies, or you can store n copies of your register and compare those n copies. This idea is called redundancy, right? basically you're storing, instead of having a single register file, you have multiple copies of the register file. Register file 1, register file 2. Logically, they're the same thing. Physically, they're at different locations. And register 0 is here, register 31 is here. Duplicated register 31. And whenever an instruction writes to a register, it writes to both of these register zeros in the two registers, right? In the two register files. And when you read from the register file, you want to ensure that the value did not change because of a hardware error or some cosmic particle struck the register file. So how do you do that? Basically, when you read, let's say the instruction is reading from register 2, it can read both copies on register 2 and do a comparison, right? If both copies are equal, then the hardware can assume that the value did not get corrupted for some error. Yes?
If they're not the same, how do you know which one's right?
So if you have two copies, you don't, right? So this is called dual modular redundancy. You basically replicate the module twice. You can only detect an error this way, right? Actually, you cannot detect all errors, right? What if the same bit flipped in both copies? If that doesn't happen, you can detect errors. But you can go to the next step, if you will, have triple modular redundancy, and have another copy. Right? Now you read 3 copies of R2, and you do a voting. You have a voting circuit that takes the 3 copies and picks the common value and assumes that that's the correct value. Right? So this way you can actually figure out which one is correct. Again, nothing is absolutely correct, but the probability that all values or multiple values will have the same error at the same location is unlikely. Right? Make sense? So you can actually extend this, right? You can actually do n modular redundancy. Of course, your hardware cost increases, but your fault tolerance also increases as you go down this way. So hardware cost increases, this is bad, but fault tolerance also increases, that's good, right? So these techniques are actually employed in some processors. It used to be that very safety critical systems or mission critical systems employed this sort of things. For example, if you're designing an aerospace controller, you could do this at different levels. And there were computers designed with multiple register files. Or even there are computers designed this way. You have a CPU, and you replicate the CPU. Right? This was one of the early designers of this was tandem computers. And they designed these for financial institutions. I assume they sold it somewhere else also. The idea is, basically, when you execute an instruction, before you make the results of the instruction visible to the architectural state, before you write to the register file or memory, you check result from CPU 0, result from CPU 1, and only if they're equal, then you write the result to the register file or memory, make it visible to the architectural state. This is a common technique employed, and you have a dual modular redundant CPU in this case to tolerate any error, right? So if there's any error that happens in one of them, you can detect it. The only thing you cannot detect is, again, the same error that changes the same bit in both results. And this is called a common mode error, if you will. And again, here, you can only detect the error, right? If you have a third CPU, now you can do voting and pick the value that's more common. If 2 of the values are the same, you can pick that one and write to the register file. So how did they use this? Actually, it turned out that they had these mainframes in big machine rooms, and when two CPUs disagreed in an answer, an LED would light up in the machine room, saying that this machine is faulty. So the operator can walk around, look around, and look at which LEDs are lit up, and replace the machine that has the LED lit up. So this turned out to be very useful in operational maintenance of what you would call a data center of today, right? It used to be the mainframe centers of the 1980s. So this is circa 1981. Okay. Anyway, I guess we got distracted a little bit, but these are fundamental computer architecture concepts also. It's how do you, if your hardware is not reliable, how do you ensure that it looks like it is reliable? Okay, so let's get back to pipelining after reliability. Do you guys learn about these concepts in any other courses? Reliability? Which course? Which one?
Distributed embedded system.
Oh, okay. Do all of you take it? No. Okay. There you go. Okay. So we covered a bunch of things in pipeline design. Today we will cover more of control flow and how to handle exceptions and interrupts. And if we have time, we will look at how we can improve pipeline throughput even more. This was last lecture. We talked about control dependence handling. This is just to set the stage, delayed branching, fine-grained multi-threading, branch prediction. So you should all know these concepts very well. How we do it at compile time, always not taken, taken, backward taken, forward not taken, and profile-based. So you should know the pros and cons and how do these work. And we talked about dynamic branch prediction. We talked about last time predictor. We added hysteresis to it because we didn't want to change our opinion just based on a single inconsistent outcome, if you will, inconsistent prediction. Then we talked about global branch correlation. We talked about the concept that branches, different branches, outcomes are correlated with each other because of the code constructs. And we designed a two-level global predictor. I'll briefly go over that and then continue with the local branch correlation. Actually, we talked about branch correlation, local branch correlation as well. And these are two different reasons for predictability of branches with longer histories. So today, I'll wrap up branch prediction, and I'll talk about several other ways of handling branches, predicated execution and multipath execution. We briefly touched upon these. Then we'll talk about precise exceptions, and if we get to it, out-of-order execution basics. So for your exam, I'm hoping to finish at out-of-order execution. So that will, whatever we cover in Wednesday will be included as well. If I'm still alive then. I'm a little bit under the weather, so. Okay, so this is just to motivate you a little bit. We've seen that even with 95% branch prediction accuracy, with a deep pipeline, 20 cycle branch resolution latency, and if you're fetching 5 instructions per cycle in a superscalar machine, remember superscalar machines, if you're doing multiple instruction fetch at the same time, if your branch prediction accuracy is 95%, basically you're fetching 100% extra instructions. And most of the time, well, not most of the time, half of the time you're spending on the wrong path. The fetch engine is fetching 100 cycles on the wrong path, even though you only need 100 cycles to fetch from the correct path. Right. So this is very bad for both performance. If your prediction accuracy was perfect, your performance would double, and your energy efficiency would likely increase significantly, right? At least at the fetch engine, because you don't need to fetch that many extra instructions. And this problem becomes worse as you increase this 20, and as you also increase the width of the superscalar pipeline. Let's say you want to fetch 8 instructions per cycle. And of course, as the number of, as the frequency of branches increases in the program. Right? Okay. So this was the realization for global branch correlation. A branch's outcome can be correlated with other branches' outcomes. And we were looking at this. So the reason, as you can see, this is just to I'm just flashing these so that you remember the last lecture. Here, obviously, there's some correlation. This branch's direction is dependent on this branch's direction, right? Similarly here, and similarly here. So to capture this, basically, we designed a global branch predictor. We associated branch outcomes with global taken, not taken history of branches, right? And make a prediction based on the outcome of the branch the last time that history was encountered. So how do you do this? Let me actually go here. Basically, you have a register called a global history register. And all it records is where did the last n branches directions. So let's say you have a 4-bit global history register. You can keep track of the direction the last 4 branches went. And it could be 1, 0, 0, 1. Well, let's make it a little bit asymmetric. 1, 1, 0, 1. And this could be the last branch. Where did the last branch that's executed go? When 1 could be taken, 0 could be not taken. Where did the last nth branch, last 4th branch, previous 4th branch go? And for this history, we associate a counter, if you will. When this history was encountered last time, when the last 4 branches outcomes were taken, taken, not taken, taken, the next branch we saw could be taken or not taken, right? We could have a 1-bit. You could have a last time predictor here. What was the outcome of the branch that we saw when we saw this history the last time? It could be 0 or 1, right? And of course, you could still have hysteresis for this particular history as well, right? The last time you saw this history, outcome could be always taken, for example. But what if the last time you see this history, the outcome fluctuates? So you don't want to change your decision. So you can also have 2-bit counter predictors in this table. Does this make sense? Okay. Any questions? So this is called a pattern history table. Yes, I'll take your question. Yes?
So how do you choose a good depth of your last C branches? Because depending on the exact width of that, you can either match the pattern exactly or be just off and have even worse accuracy.
Exactly. So that's a very good question. It's an empirical design, and there are papers that analyze that. There are many papers that analyze how do you choose a good depth. Usually the way it's done in industry is you have a set of workloads, and you design your pipeline, and basically you have a simulator, timing simulator. You could just simulate the branch predictor, actually, and basically run your workloads for different history lengths and figure out the prediction accuracy. Normally, as you increase this length, your prediction accuracy increases because you're capturing more correlation into the past. But there's one downside, of course. As you increase this, now your training time also increases, right? Because if this is only 1 bit, then you can train very quickly, right? You're just looking at 1 of these locations or 2 of these locations. But if this is 16 bits, then you have to see the same pattern, if you will, multiple times to be able to train, to be able to figure out whether or not, whenever I saw this pattern the last time, or how many times, where did the branch go? Does that make sense? So there is a trade-off. Yes?
Isn't there a lot of hardware overhead just evaluating the pattern, so finding patterns in the last 6 weeks or so?
Finding patterns. So you're not finding patterns here, right? So what this predictor is doing is it's taking this history, and using this history you're indexing this table.
Okay.
So if this is 4 bits, this table is 16 entries. Right? And this 16 entry here tells you where the branch went. You know, when you saw this history last time. Yes?
If 16 entries, it was getting really big.
16 bits.
Oh yeah, if you have 16 bits, yes, then it's to the 16 entries in that table. You're right. So if this is n bits, basically, this is to the n entries. And it does get big. There's another trade-off over there. It takes longer to access in that case, and it becomes more costly. Right? So that's why you may not have 16 bits. But we will see some real processors and these numbers soon. Okay? Yes?
This is all hardware level?
Say it again?
This is all hardware prediction?
This is all hardware, yes. This is all hardware. Yes?
In a lot of cases, wouldn't it be better if we had certain applications store this data for a particular, let's say using Word, and for Word, the particular history for that user was in a particular way. So, wouldn't this function better if the software that was working on top of it took advantage of this?
So somehow you're saying software sets these bits in this table.
Saves them from one execution of a particular program to the next.
So people have proposed that. People have looked at all kinds of variants of this predictor. For some applications, if you really know, again, at software time, at compile time, that for this history, your branch will go one way or the other, then that could be a good idea, right? Then you don't need any training. But if the behavior changes, for example, sometimes when you see this history, you go taken. Sometimes when you see this history, you go not taken. And maybe you flip, right? And you could construct some cases potentially if you write some code. Then the software cannot set the bit correctly, right? Then you need really dynamic branch prediction. So this table can be set by software or compiler, or can be adaptive, as I showed here. It's a table of 2-bit counters, right? Or it can be dynamic, adaptive. And you again have the same trade-off of compile time versus runtime trade-off, right? Yes?
So I'm a little confused. Does this have entries for all branches of a particular program, or like one histories for one branch?
It has entries. There is no branch here, right? These are the, where did your last n branches go? Taken, taken, not taken, taken.
So just history for the whole program?
Yeah, history for the whole program. That's the simplest global predictor. But as I discussed last time, what Pentium Pro did, it had separate tables. Like it had 4 tables, which you would access in parallel and pick based on lower bits of the branch PC. So you could partition this table in a sense. Right? So that, and the goal is to eliminate interference, because sometimes different branches go different ways based on the history, right? You could imagine this. And if you have a single history, if you have a single pattern history table counter for a given history, then you cannot distinguish between that. And what Pentium Pro did was, it had 4 different tables, and based on the lower 2 bits of the program counter, you would pick which one to use, so that you can eliminate the interference between different branches. And what does interference mean? Essentially, 2 branches may go different ways for the same global history, right? And you would like to distinguish between that, if possible. Okay? Okay. Okay, let's move on. So this is an example you can study that shows how the global predictor works. This is the global history register, GHR, I called it here. And basically you have an inner loop that gets executed 3 times, I think, yes. And you have an outer loop that gets executed 100 times. And every time you execute this branch here, the result is dependent on the history of both branches. Right? So if your global history register is 1101, then the result of this branch is taken. 1011, again, is taken. 0111, it's not taken because this loop has executed 3 times, right? And if it's 1110, it's usually taken because you're testing this value. That's this branch here. So you can study this on your own to make sure you understand it. This is similar to what I showed on the board last time. Remember, these are still review slides, so I'm warming you up. Okay? So Pentagon Pro branch predictor, we already covered it. It's essentially this with 4 different pattern history tables that is selected based on the program counter. So how do we improve global predictor accuracy? So Pentagon Pro did something to improve the global predictor accuracy. It wanted to reduce interference. The designers wanted to reduce interference between different branches, so they separated the pattern history table of different branches that happen to have different bits for bit locations somewhere in the program counter. And we don't know where because they don't disclose it. But there are other ways of improving predictor accuracy and using also context information. I'll just give you the idea. Instead of using just history, one thing you can do is you can put more context before indexing this pattern history table. So here we were saying, where did the branch that I'm going to execute go the last time I saw this history? But you could also do this. You can take this history and take some bits from the program counter, let's say 4 bits from the program counter, and XOR them, and then index into the pattern history table. In a sense, this gives you a context of where you were last time. The last time I executed this branch, this program counter, and I saw this history, somehow I summarized that information by XORing these 2 values, the branch went this way. Does that make sense? So this is a way of adding more information into the indexing function so that you know more of context of when you did the prediction. And that's the idea here. You have the branch address, branch history, register, you XOR them, index into the pattern history table. So you get more context information, so your prediction accuracy increases. You also get better utilization of this pattern history table, if you will. So if you think about it, if you have only one value indexing into the table, you could always be mapping to the same place. For example, a lot of the branches are taken, right? You can have 1, 1, 1, 1. All of these will map to the same location, right? If you had only the history. Whereas if you also use 4 bits from the PC, you would distinguish between those branches because they would map to different entries in the pattern history table. Okay, that's the idea of better utilization. Of course, downside is now you've increased the access latency of your branch predictor, right? You have XOR gates before you access. And we will see why this could be an issue a little bit later in the lecture. Okay. By the way, this is a good paper to read if you're interested in this. It gives a lot of examples of how different branch predictors work, global, local, with code examples. Okay, so let's summarize a little bit what we covered. Remember this picture? We had the branch target buffer and the direction predictor. A one-level branch predictor, essentially you use the program counter to get the target address, and in parallel, using the address of the branch, you look at the direction predictor. This is a last time predictor, for example, and with 2-bit counters it uses some hysteresis. If the direction predictor says taken and you have a BTB hit, then you get the target address. Otherwise, you use the PC plus instruction size as the next fetch address. 2-level history predictor, again, this part remains the same. Now you have global branch history to index into the direction predictor, but you still need to index into the BTB with the program counter to get the target address. 2-level G-share predictor, basically you XOR the program counter with the global branch history to index into the direction predictor. Make sense? So just to give you we're going to talk about indirect branches later on. Indirect branches may take multiple may have multiple targets, right? So it may not make sense to index the BTB for an indirect branch. It may not make sense to index the BTB with just the program counter, right? Because it'll always give you the last target. Unless the last target is the same as the current target, you're going to predict wrong. So there have been predictors that are designed to predict just indirect branches. Remember, indirect branch, register indirect, essentially jump to R3, or you're jumping to the address at R3. You could imagine a branch target buffer for indirect branches that is indexed using the program counter XOR the branch history. Last time I saw this branch, this indirect branch, and it had this global branch history coming into it. The target was this. So this time I'm going to predict the target will be the same as that time. Does that make sense? So now you have context information about the indirect branch. How did you get to this indirect branch? Essentially, that's what the global history register tells you, right? What path did you take in the control flow graph of the program to get to this indirect branch? And you can record the target address you saw at that path, perhaps XORed with the program counter. And the next time you see the branch, you're going to predict the target address to be the same. And assuming there is that kind of predictability in the behavior of the indirect branch target address, you'll get it right. And it turns out this provides significantly better performance compared to predicting the target as the target of the last time you executed the branch. Make sense? Yes?
I didn't understand why do we need to predict it, because we have the data right there in the register.
But remember, you don't access the register.
Right.
Oh, why do you need to predict it?
I'm talking in terms of latency of getting the data.
Okay.
How different would it be?
Oh, I see. So we have the data for this branch in the register, you're saying. Well, that depends on where you access the register file in your processor, right? If you access it very close to the fetch stage, then you'll have some bubble, right? But when we cover out-of-order execution, you will see that there could be like 20 or 30 stages, plus the data could be, this could be dependent on some cache miss. So it could be hundreds of cycles until this data is available. Okay? In a very simple pipeline, if you access the register file, the next cycle after you fetch the instruction, then branch prediction doesn't help you that much, right? Indirect branch prediction. Okay. Okay, so let's look at the local branch correlation. I think you got the idea from last time. But the idea here is a branch's outcome can be correlated with the past outcomes of the same branch. And this is the idea of local branch correlation. So if you look here, you have, this is the pattern that I've showed you before, I think. You have a loop that iterates 4 times. And if you see this pattern, 1, 1, 1, 0, that pattern is repeated for this particular branch, right? You basically keep executing the branch as taken, 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 not taken, 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 not taken. Of course, this assumes that you come back to the loop later. So if you just look at the history of this branch, it's 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. So if you keep that history, you know where the branch will go the next time, right? Based on the history. That's the idea. So how do you capture? Well, have a per branch history register, right? And associate the predicted outcome of a branch with the history, taken, not taken history of the same branch. Before, all of the branches were updating this. Now we're going to have only one branch updated. Of course, we're going to run into hardware issues, right? You can imagine. And you make a prediction based on the outcome of the branch last time the same local branch history was encountered. This is called the local history predictor, or local branch predictor. And again, we're using 2 levels of history, right? We're not just looking at the last time. We're looking at last n times. Yes?
So you would only use local or global, but not both, right?
We'll get to it.
Okay.
You could use both. And actually, the modern machine use both. Because these are different types of predictability, if you will. So, okay, how is this different from the global predictor? Well, one implementation is like this. Basically, you have, instead of having a single register updated by all branches, you have a bunch of local history registers, right? And that's the idea here. So how do you index into it? So this is a table of local history registers. Table of local history registers. And remember, we want to do this per branch. We want to keep the history per branch. So we need the program counter, right? So basically we take n bits from the program counter, index into this table. Of course, this table now has 2 to the n local history registers. Those branches that have the same value in the program counter for those n bits will map to the same local history register. So there will be interference, right? And so this will be your history. And let's say this is m bits. You keep track of what happened to this branch at PC, this location, the last m times it was executed. And you can use this history to index the pattern history table. And the pattern history table, let's say this is 1 bit. The last time you executed this branch, the last n times you executed this branch, the history was this, and for this history, the branch was taken or not taken, right? Make sense? So we just extended the single global history register, now we are making it local. Ideally, you would have a local history register for every single branch in the program. But is this possible? Yes?
So do you have multiple pattern history tables also then for each branch?
So yes, it makes sense to have multiple pattern history tables, right? But then you're increasing hardware costs as you add multiple pattern history tables. And you can do the same thing Pentium Pro did, right? You can get predictions from different pattern history tables and pick the one based on some bits in the program counter, right? And again, you could have this per branch, but then you cannot have a table. You cannot have a single counter for every branch in the program. You cannot have a table for a pattern history table for every branch in the program. Well, I guess it depends on your program, but for any program in the world, you cannot guarantee that, right? Because someone can write a program with 1 billion branches. You're going to have a table that has 1 billion entries. So you have to limit the size of the table because of hardware limitations, which increase, again, the interference in the tables. So multiple different branches will map to the same local history register, and you may not get perfect prediction because of that, right? Even though your branch may be perfectly predictable. For example, your branch may be this, right? Here it's perfectly predictable. If you dedicate a 4-bit local history register for your branch, you can get 100% prediction accuracy for that branch. Except you may be unlucky and some other branch can map to the same location, right? And that may not be perfectly predictable. In fact, that may be going the other direction. Okay. So now you know the idea of local branch prediction. So if you look at the local history predictor, it looks like this. Basically, with program counter, you index this local history registers, get the local history, and using the local history, index the direction predictor, basically pattern history table, that tells you what happened to this branch the last time you saw that local history for that branch, and you also access the target address. Okay. Okay, so your question was, do you have both of them? We looked at local history, we looked at global history. Now, if you think about it, these are different kinds of predictability, right? Some branches may be perfectly predictable with a local history predictor, and some branches may not be. May have no correlation, but they may be perfectly predictable with what happened to the previous branches, right? Remember the global correlation? You have if condition 1, do something. If condition 1, I guess you could think of it this way also, do something else. Now you can perfectly predict this branch based on the behavior of some other branch. Although this may have no predictability based on the outcomes if you look at the local history of this branch, right? Because the conditions may have no predictability if you look at over time. But if you know the condition of this branch, then you will know the condition of this branch. Yes?
I don't understand what's the benefit of the secondary reference. Like, why don't you just put the taken information in your first table that's indexed by bits of the PC?
Why don't you put, you mean here?
Yeah.
You mean taken or not taken?
Yeah.
So, because you can actually have counters here, right?
But why can't you just put the counters in previous? There's just too many of them.
So what do you mean?
Like
So the history can change, right? So this is not, so you want, so for this is telling you what is the local history for this branch. It could be 1, 1, 1, 1, 1, 1. The next time you see it could be 1, 1, 1, 1, 0. Right? So you really not need different counters or different information.
But I mean, are you going to have like lots of interference? Like if I have 1, 1, 1, 1, some I throw in that, and 1, 1, 1, 1, and some J throw of that, then I'll point to the same thing in this other table.
So if you have 1, 1, 1, 1 here and 1, 1, 1 here, you're saying? Yes, they will point to the same table, but you can solve that problem by having multiple pattern history tables.
Oh.
Right? So you cannot put the counters here because you want to figure out whether you're taken or not taken based on the value of your history, not value of your PC. Right? If you put the counters here, then you associate the
Like
prediction with the PC, not the history. That's why you have two levels, right? That becomes one level.
Yeah, because you want the PC across the history.
Exactly. Okay. Okay, so local and global are two different predictability, so the idea is if you want both kinds of predictability, why don't we combine them, right? Basically use more than one type of predictor, multiple algorithms, and select the best prediction, if you will, for a given branch. And you can learn this dynamically also, potentially. Right? So, well, I'll give you a picture of this, but so what you can do is you can have one predictor like this, your program counter, and history for that program counter, and the pattern history table. Where did the branch go for that program counter? This is your local prediction, right? And you could also have your global predictor. Global history register, indexing into the pattern history table. And you can make two predictions and pick the one that makes sense. So how do you pick the one that makes sense? Well, how do you design this control of this mux? Well, I'll show you one example, I think. This is the Alpha 21264, which was one of the fastest machines of its time. And existing machines use similar tables like this. But actually, this is essentially the same thing I showed you here. You get a local prediction, and you get a global prediction. And you choose between them using something called a choice predictor. And it turns out the way they did this choice predictor was, the last time I saw this global history, was the global predictor doing better or the local predictor doing better? So you keep a record of which predictor was better for this particular history, which predictor was correct for that particular history, and choose the predictor that does well on that history. You can imagine other ways of designing this, right? You can do it based on program counter, for example, or you could do based on program counter XORed with global history, more context information. So, but that's the design choice they made. Yes?
It seems like we're adding a lot of logic. Doesn't that actually reduce the clock speed, even though we're going to increase the cycles per instruction? I mean, reduce the cycles per instruction, but it's going to increase the clock speed.
Yes, that's an excellent point, and people should be wary of this when they're designing this, because if your critical path increases, now you're reducing your clock speed. And absolutely, you're right. In a lot of the machines, fetch engine is part of the critical path. So you're going to be very careful. So they size these tables very carefully such that they did not increase the clock cycle. And of course, sometimes you may want to size up, you may want to increase your clock cycle a little bit because you gain a lot more in cycles per instruction, right? Again, that's the trade-off they made. But in that machine, minimum branch penalty was 7 cycles, and typically they saw 11 cycles because it was an out-of-order execution machine. And this was their branch predictor. you can imagine other kinds of predictors feeding into this. And in fact, there are other kinds of predictors. You can have a simple last time predictor, right? Feeding into this. And what would be the value of that? This last time predictor trains very quickly, right? You don't need to learn the history. You don't need to see the history for a while. If you look at this, the history is relatively long. It's a 10-bit history here. And global predictor against the 12-bit history here. Okay. So what is the advantage of hybrid branch predictor? Essentially, you get better accuracy. You can use different predictors for different branches if you can learn which branch does better with which predictor. You also reduce the warm-up time, if you will. This is what I mentioned here. You can have a faster predictor that warms up faster. And while that predictor is doing well, you use predictions from this predictor. Right? Because here, warm-up means essentially whether the predictions are actually warmed up. Here, you don't need that much history. Right? If your history is 12 bits, you have to see that branch at least 12 times for the local history. Make sense? Well, actually, it's more than 12 times because you have to populate this table, right? You have to learn this table. It's a lot more than 12 times. You have to see the histories that are common in your program at least several times so that you warm up the 2-bit counters here. And I think they had 2-bit counters in alpha. Looks like they had 3-bit counters for the local history. For the global history, they had 2-bit counters. Okay, so you reduce the warm-up time because you can use the prediction from a faster warm-up predictor while another predictor is just learning the behavior of the program, if you will. Disadvantages, now you need a meta predictor or selector, which is logic here. And now your access latency is longer because you have a mux here. And you're increasing the access latency of your predictor, right? Okay, so these are implemented in real machines. If you look at Pentium 4, it has a similar predictor. In fact, it has more predictors feeding into this. Yes?
So for the level predictor, the value stored in the first table, is that the history of like the previous n branches, or is it the history of this branch the previous n times? Yes,
that's the history of this branch at PC x previous n times it was executed.
Seems like you would want the other one though, because
this is the other one.
Yeah, but it seems like maybe you would want that one within this, so that way you get.
Yeah, you can design another predictor, right? Exactly. So maybe you should design these predictors that take a look at their accuracy. It's an art. It is true. It's not clear exactly how you design it, but you can use many different information, right? For example, you can use, I don't know, you can come up with something else to index the predictor. What can you think? For example, your call stack depth. That could affect your predictability, right? Where are you in your call stack? What function calls you've executed? Instead of just taken or not taken. You could, some other people have proposed, instead of using this history register, 1 bit per branch. Let me just give you the idea. Instead of 1 bit per branch, you can do this. This is called a path history predictor, if you will. Instead of taken or not taken, you take 2 bits from each PC program counter. These are essentially what were the 2 bits of the last n program counters, n branch program counters you've seen. This gives you the path, if you will, because now you can distinguish between different branches that are in your history. So that gives you more information, potentially. Okay? Okay. So one other thing they did here was they reset the predictor tables on a context switch so that they don't use predictions from a different program. Yes?
Is there a good rule of thumb of when ultimate optimization sort of takes its toll so that the clock cycle getting sort of takes away from branch accuracy?
Oh, takes away from the gain you get in CPIs. Well, there is no good rule of thumb, really. It's really how long it takes to access these structures and where your critical path is. It's the critical path design again, right? Okay, so let's take a look at an example. This is actually very old data, I think. But this is the branch prediction accuracy, and this is not local global, unfortunately, but bimodal is essentially a last time predictor with 2-bit counters. That's called a bimodal predictor. 2-bit counter last time predictor. This is G-share is what we've seen before. This essentially, PC XORed with history. And this graph shows the conditional branch prediction accuracy for different spec applications, and these are really old applications. So if you look at the predictability, this is the first bar is bimodal, the second bar is G-share, the third bar is a predictor that combines both of them. And if you look at the average, bimodal by itself, which is 2-bit counter last time, gets about 92% accuracy. G-share increases that to 94%, and if you have a combination of both, you get around 96%. Yet still, it's not enough as you increase the pipeline depth, right? Or the width. And you can see that some applications are hard to predict, like GCC. They can benefit from combining the 2 branch predictors, because neither of the predictors alone is doing well. Well meaning 85% accuracy. But if you plug in the 85% accuracy number to the slide that I showed you to motivate you earlier, you'll get a horrible execution time, right? So you can actually calculate how much execution time improvements you get going from 85% accuracy to 90% accuracy in that particular machine, and you'll see why people have optimized these predictors over time. That could be a good homework question or an exam question. Okay. Well, I guess we're going slowly. Maybe I'll let you take a break for 5 minutes. Is that good? So let's go back, get back at 1:28 p.m. So we've covered branch prediction. That's one way of handling control dependencies. That's a very powerful way. All machines today employ it. Well, all high-performance machines, but even low-performance machines, because you save energy in a sense. Another way of handling branches is predicated execution. We briefly covered this, right? Why don't we eliminate the branches instead of trying to predict them? That's the idea of predicated execution. And basically, the idea is to have the compiler convert the control dependency into a data dependency. Right? And we'll see how this is done. And the ISA, each instruction in the ISA has a predicate bit. This predicate bit is set based on the predicate computation, if you will. And only instructions that have the predicate bit set to true take effect. Otherwise, they turn into no-ops. That's the idea. It's a very powerful and simple idea. And let's take a look at a simple code example that implements this. So this is a simple if and else branch, right? If you look at the normal branch code, what you have is you compute the predicate based on a condition, and based on the predicate, if you will, if the predicate is true, you jump to target. If the predicate is false, you jump to some other location. Here, instead of doing the jumping, we're going to associate the predicate with each instruction here. So B has an instruction, and C, the basic block B and basic block C has instructions. And instructions take predicate registers, if you will, meaning another register source. And in this case, this instruction is supposed to execute if predicate 1 is false, and this instruction is supposed to execute if predicate 1 is true. Yes?
Isn't this basically what the ARM does?
Exactly, yes. I mean, we will go to ARM. We will cover ARM. So how many of you know the ARM ISA? Sort of. Quite a few of you. Okay. So this is the same thing as conditional execution in ARM. ARM calls this conditional execution. Every ISA vendor has to rename what's done, but this is called predicated execution. It is true, it is conditional execution also, right? You're executing an instruction based on a condition. If the condition is true, instruction is executed. If the condition is false, instruction is not executed. That's the idea. And there is an instruction that sets the conditions. Basically compare instructions, for example, can set the condition. So the idea is this predicate is really a data dependency now, right? So you're really not branching in the code, but you need to satisfy the data dependencies. So this here, there was no data dependency, right, between P1 and the move instructions. There was no data dependency. Now the move instruction is really dependent on P1. Make sense? Which means that now you have straight line code. You don't have a branch. Which means that you don't have anything to predict. Right? You can fetch the straight line code. Which means that you know what instructions to fetch next, even when you see a branch. Well, there is no branch, right? The branch is gone. So branch problem is eliminated, right? That's a great solution. What's the catch? Okay, you cannot eliminate all of the branches. What if you are jumping backwards, right? And think about whether you can eliminate those. But that's absolutely true. Yes?
The condition isn't satisfied, you have a no-op.
Exactly. So even if you can eliminate the branch, you're doing additional work always, right? Let's say this branch was 99% predictable, 99% of the time, or 100% of the time it was taken. And you turned it into this predicated code. If you had a branch predictor, maybe a simple last time predictor, you would get 100% accuracy here. Which means that you would execute, you would never execute the code in B, because you would jump around it. Whereas here, it doesn't matter what kind of prediction accuracy you would have gotten, you're always executing both paths. And if you had 100% prediction accuracy, you're always executing something you should not really execute. Right? So you can actually reduce performance this way, right? If you do not do it for the right branches. So to refine the idea, this is a good idea for branches that are hard to predict. So if you can somehow identify branches that are hard to predict, and if you can convert them into predicated code, then you can get significant benefits. But if the branch is really easy to predict, then you can reduce performance because you're always doing additional work that you're going to throw away. Yes?
In general, would, even if you're doing ops, would like this strategy be saving power?
It could be saving power, but it could also be increasing power. Why do you say that? Let's say, again, let me take the example of 100% prediction accuracy.
Well, I guess assuming you take it 100%.
Okay, 99%. You can do the calculation. Actually, this could be an interesting question. So 99% of the time you're correct, let's say. Then you are executing only what you're supposed to execute 99% of the time, right? Whereas 1% of the time you have this additional flush penalty with the branch. Whereas here, 100% of the time you're executing things that you're not supposed to execute. So you can actually do the calculation. Let's try to at runtime come up with a model for this. And this is what compilers do, and they just try to decide whether or not to predicate some branches. So what is the calculation? Right. I guess, let me see. So how many instructions, how many slots do you waste, if you will? I guess slots wasted could be one metric, right? Instruction slots wasted. If your branch prediction accuracy for a branch is 99%, you mispredict only 1% of the time, and you execute, basically you incur the flush penalty 1% of the time. Let's say your flush penalty is 20 slots, right? Or what did we say our flush penalty was? 20 slots, yeah. So you waste 20 slots 1% of the time, right? If you predicate this code, now you have to look at how many instructions you're really wasting, right? Whenever you, always. So I guess I'll say waste 20 slots 1% of the time. Here, you're going to waste, I don't know, let's say you have 5 instructions under B. 5 instructions 100% of the time, right? you execute the branch. Now it depends on how often you execute the branch now, right? If you execute the branch, well, I guess it doesn't depend on that, does it? So this is a bad idea in this case. Is that correct? You're wasting 20 slots 1% of the time versus you're wasting 5 instructions 100% of the time. So if your branch prediction accuracy is really high, this idea is not good. So then the question is, what should your branch prediction accuracy be for this to make sense? Right? And that's the idea. For hard to predict branches, where hard to predict is dependent on a bunch of values here, how many slots do you waste if you predict incorrectly? And how often do you predict incorrectly? And how many slots do you waste when you convert the branch into predicated code? Based on that, you can do a calculation and figure out what should your prediction accuracy for this branch be for it to be profitable to be converted to predicated code. Yes?
Also, that's just a really big basic block to do this for. Like I used to see you only do like C moves if you have like 1 or 2 instructions.
Mm-hmm. So, well, you could do it for big basic blocks, right? If your branch prediction accuracy is 50%, for example, it may make sense to do it for big basic blocks. So it is an equation, basically. What is the cost and what is the benefit? What is the cost of branch prediction and what is the cost of converting it into predicated code? Okay, so you mentioned CMUs. Many ISAs actually employ a very limited form of predicated execution, and that's the idea of a C move. What is a C move? Essentially, you conditionally move one register to another if the condition code is true. The condition code you're testing is true. So that's basically it. You've probably written this kind of code in C, right? This is employed in most modern ISAs. Well, modern, if you will. x86, most common modern ISAs. x86 does this, for example. What is the downside of this? Well, now you have 3 sources, right? That's one downside of predicated execution. Each instruction, instead of having 2 sources, now you have a 3rd source in the instruction. So you have to source that from somewhere. Okay, so just to motivate you, this could actually be high performance and energy efficient, as you suggested, if you do it for the right branches. So if you look at a deep pipeline, if you use predicated execution, what happens is, let's say you fetch both paths, A, B, C. Well, for predicated execution, actually, this should have been laid out. B and C should be the same basic block, because you eliminate the branch. This is what happens. When you execute the branch and figure out that it went to C, B becomes no op. If the branch had gone to B, then C becomes a no op, right? Whereas if you do branch prediction here, you get a full pipeline flush. Okay, so let's cover the advantages and disadvantages of this. Well, you can eliminate branch mispredictions for hard to predict branches, right? That's the biggest advantage. No need for branch prediction for some branches. And it's good if misprediction cost is greater than useless work due to predication. There's another advantage that you may not have thought of. This actually, now you get a straight line code, right? You eliminated the branch, which means your compiler can do more optimizations in the code because the branch is gone, so you don't have this control flow dependency hindering the optimizations of the compiler. Now it can reorder the code from a bigger region. Okay, disadvantages, well, we've already covered this. It causes useless work, especially for branches that are easy to predict. Right? Well, it always causes useless work, but this becomes bad for branches that are easy to predict. And it reduces performance if misprediction cost is less than useless work. One other downside is, remember, this is done by the compiler. It's a static technique. Well, I guess there should be a faster way of skipping it. The compiler generates the code this way, using the instructions of the ISA, which means that if the branch prediction accuracy changes over time, you cannot adapt your code, right? So you may decide to predicate a branch, eliminate the branch, because the compiler profiled the code and figured out the branch prediction accuracy is terrible for this branch. But that's based on profiling. Right? So if you later find out dynamically that the branch prediction accuracy is actually great, well, your code is already predicated. So you're going to waste waste work because of this. So this is a big disadvantage of predicated executions. It's not adaptive to runtime branch behavior. And as we've seen, runtime branch behavior changes based on which control flow path you've taken. Well, we haven't seen the input set, but you can imagine that the branch, you can execute some loop 10 times versus 20 times based on your input set, right? Yes?
So how big of an advantage is it to get rid of all the hardware that does branch prediction? Is that a significant amount of hardware? Or is it just
No. Well, it could be significant because it complicates your front end. So it helps, yeah. So I guess that's another advantage you're saying, basically. You could eliminate, if you could. The issue is it's very difficult to eliminate all of the branches. So there are some branches that you cannot, well, I guess additional hardware and so you will eliminate some hardware. I guess I should, you can put as an advantage, you can potentially eliminate the branch prediction hardware. But it cannot be done easily because there are other branches that are remaining, even if you do predicated execution. And also, predicated execution has additional hardware and ISA support, right? It's actually relatively significant ISA support. You need the predicate registers. And now you need to source 3 values for an instruction. Yes?
You're also trusting the compiler again.
Well, hopefully the compiler is generating correct code. But yes, that's right. You're always trusting the compiler whenever you're changing your ISA interface, right?
The hardware wouldn't be fault tolerant.
Hardware wouldn't be what?
Fault tolerant.
I didn't understand that.
If the compiler generates wrong code, the compiler would be able to handle it. So,
Oh, sure. I mean, if the compiler generates the predicate bits wrong, then you cannot do anything, right? But I mean, that's kind of similar to compiler can generate the branch targets wrong also, right? Okay, so it cannot eliminate all hard to predict branches. Loop branches are very difficult to eliminate, or I would say impossible to eliminate. And also, because of this, compilers usually don't eliminate all branches because things are not as nice as if and else, right? If you write a program, this is not the only thing that you do, right? You have very complex control flow graphs in the program, and it becomes very difficult to eliminate all of the branches. Okay. So Intel Itanium processor had predicated execution, and they actually have a good paper that describes that they gained 1.4% performance improvement, I think, by using predicated execution in their processors compared to not using it. So it didn't work out very well for them. It complicated their design significantly for 1.4% performance improvement. But this maybe depend on their compiler technology also. Basically, each instruction can be separately predicated, and they had 64 1-bit predicate registers, which means that each instruction carries a 6-bit predicate field also now, right? So your instruction size increases. And, well, you can see this. Well, looks like many of you know the conditional execution in the ARM ISA. Almost all ARM instructions can include an optional condition code, and instruction with a condition code is only executed if the condition code flags in the processor status register meet the specified condition. So these are some slides I stole from ARM. But if you look at the ARM instruction format, all of the instructions, the top, 4 bits, are dedicated to the condition code. Right? This specifies when this instruction should take effect, which is essentially a predicate. Right? So you can have 16 conditions, and these are the conditions. Always. Well, if you want the instruction to be executed always, you'd better set those condition bits to 1110. That way the instruction is not dependent on a predicate, meaning condition register. So ARM has condition codes, so you need to check the condition code. So for example, if the condition bits are 0000, this equal condition code is set, which is Z condition code. If the Z condition code is set, then the instruction is executed. Otherwise, the instruction is not executed. Make sense? So if you've seen ARM, it's pretty simple. It's one form of predicated execution here. And you can see how these bits can be set. For example, if you have an add instruction that you always want to execute, you do add always. If you have an add instruction that you want to execute only if the 0 flag or 0 condition code is set, then you use add equal, if you will. So what does this buy you? So from some of the ARM slides, this is some code that figures out the greatest common denominator, and they show you some code that you would get with the normal assembler, if you will. Normal assembler being assembler that produces normal branch code, and the ARM conditional assembler, which uses the conditional execution provided by the ISA. So you can actually reduce the code size as well if you use the conditional execution here. Does that make sense? So I'll let you study these slides. It's relatively simple. It's the same thing as the control flow graphs that I showed you earlier, except it's a real example with the greatest common denominator. Okay, so another idea to eliminate branches, if you will, well, maybe not eliminate branches, but do something about branches, is the multipath execution. In a sense, predicated execution kind of does this at the compiler level, right? But what if at the hardware level, when you get to the branch, we start executing both paths? That's the idea of multipath execution. Execute both paths after a conditional branch. And you could do this for all conditional branches, or you could do this for hard to predict conditional branches. I guess, how do you figure out what is hard to predict? Say it again.
You see your counter perhaps if you're towards the middle.
So you could do that, for example. So this is the idea of confidence estimation. How confident are you in your branch predictor? Let me put it here. Confidence, branch confidence estimation. You can have a 4-bit counter, for example, and if the counter is really weak, you can say, oh, I'm not really confident in this prediction. Right? And for that kind of branch, you can do multipath execution. The advantage is, well, if your misprediction cost, you're doing useless work, right? You're executing both paths after a branch. If this useless work is less than the misprediction cost, misprediction penalty, how many slots you would waste, it went somewhere else, but how many slots you would waste with a branch predictor, then this improves performance. The upside again is this also doesn't require any change in the ISA. Remember, predicated execution requires some change in the ISA, whereas this one doesn't require change in the ISA. It's all done in the hardware. In one cycle, you fetch from one path, and the other cycle, you fetch from the other path. And you can keep filling the pipeline by fetching alternately from different paths. Of course, you need to make sure that these paths do not write to the same registers, right? Or you should not really forward from one path to the other path. So you got to put the hardware necessary to ensure that. Otherwise, you would get incorrect execution. Which means that, well, where is this? Yeah, each followed path requires its own, ignore this for now, I'll fix this. But its own, essentially, context, right? It really requires its own registers, program counter, global history register, right? There's also another problem. Well, you have, when the machine encounters another hard to predict branch in one path, what do? Do you do multipath execution on that again? So you can see the problem can become exponential quickly, right? Especially if you have a deep pipeline. And if you're doing this for all branches, then you have a big problem. Then you have only one path that's correct in the machine, but you may be executing two of the n paths, where n is the number of branches. So quickly you waste a lot of work with this approach. And you waste work if the paths actually merge also. So let's take a look at that. So let's take a look at dual path execution. Let's say we are going to follow only two paths. Let's say A is hard to predict. What dual path execution does is you fetch from path 1, then you fetch from path 2. Then in the consecutive cycles you fetch from these different paths. Basically you're duplicating work here, right? What predicated execution does is this, right? When you get to the control flow merge point, you keep executing only one path, because the compiler predicated only that part that was different for different branch conditions. Make sense? So this is a wasteful way of handling the branch penalty. But there could be cases again where this may make sense. In fact, yes?
So this is all just like a power optimization?
Which one? Multipath execution or predication?
Emerging.
No, this is just to contrast what happens with predicate execution. With predicate execution, you don't fetch from multiple paths when your paths are not dependent on the predicate, right? When your path is not dependent on the branch, these basic blocks are not dependent on the branch here, right? With predicate execution, what the compiler would do is it would form straight line code A, B, C, D, E, F, right? Whereas here with multipath execution or dual path execution, you go both ways. Of course, you can add hardware to figure out whether you're merged or not, right? Now that makes the hardware more complex.
But adding the hardware to determine if you're merged, is that a power optimization?
You could do that, yes. Is that just a power optimization? It is kind of a power optimization, you're right. And also performance because you're not wasting work as much, right? You could be fetching more, basically. Instead of wasting half of your fetch bandwidth, you'll fetch more later. So it could improve your performance also. Yes?
It's maybe too early to ask this question, but if you're doing like dual path, if B or C caused like some error or some exception, and like in the normal control flow, like you wouldn't hit that exception, but at the time when you execute C or B, you don't know whether or not like you're going to execute that. Well, that creates some like very difficult to find like
bugs, you mean?
Not necessarily bugs, but like potentially at a point in execution, you don't know whether or not you should continue on or stop because it's an exception that should be caught at that time.
We normally delay exceptions at the end of the pipeline, right? So, and we will see that. So maybe if that doesn't answer your question, ask me again at that time. Okay. Okay. So that's dual path. Let's consider some other branches also. We've talked about conditional branches quite a bit, but there are other branches in the world, calls and returns, for example. And you've all written calls and returns like this, probably. If you have direct calls, these are easy to predict, right? These are always taken as single target. And you can mark the call in the branch target buffer and predict the target that's stored in the BTB. So if you have a call instruction that's based on some program counter plus offset, this is pretty easy to predict. You store the target in the BTB and mark the instruction as a call in the BTB. So when you access the BTB, you get a bit saying this is a call, so you always take this target instead of PC plus 4. It's very simple. Returns are a little bit difficult. They're indirect branches, right? Because you normally return using a register value. Because a function can be called from many points in code, but then you return to the call points. Which means that a return instruction can have many target addresses, which is the next instruction after each call point for the same function, right? You have, I don't know, let's say this is your function. You have one return, and then you can have multiple calls at different points in your program that are all going to this place. So where do you return? Well, it turns out these are relatively easy to predict because of one property in the code. Usually a return matches a call. You do a call, and it has a matching return, usually. Unless you're programming with gotos, right? Unless you write a goto in your program. You guys program with gotos? You do? Okay. So what happens is usually something like this. You have nested calls, and at the very innermost nesting level, you return. And this return corresponds to the innermost call. And the next return corresponds to the next innermost call. And the next return corresponds to the next innermost call. So this looks like a nice stack behavior, right? What you can do is when you do a call, you push the return address on the stack. And when you do a return, you pop the address from that stack and use that as your prediction. That's the idea of a call return stack. Use a stack to predict the return addresses. And almost all machines today have this. When you have a fetch call, you push the return, which is the address of the next instruction, right, on the stack. When you fetch the return, you pop from the stack and use the address as the predicted target. Simple, right? And it turns out it's accurate most of the time. With an 8-entry stack, returns can have 95% accuracy. and you can increase the size of the stack, if you will. Of course, think about when this doesn't work, right? What if you overflow the stack? What if your nesting level is greater than 8? Now you really destroyed your prediction accuracy in your return address stack, right? Okay, so hopefully this is a simple concept. Well, let's cover indirect branch prediction briefly. This is an even more difficult problem because registered indirect branches have multiple targets. So this is the conditional branch. You have 2 targets. You just need to predict the direction, if you will, because target doesn't change unless you have a conditional indirect branch. That's an even difficult problem. But most ISAs actually don't have conditional indirect branches. And with an indirect jump, now you have many targets. And you get your target from a memory location, let's say. So how do you figure out that target? And this is used to implement a lot of different things, common things like switch case statements, virtual function calls, jump tables, function pointers, and interface calls, especially high-level language abstractions. Right? So, well, people have looked at many different ideas. I'll just give you 2 of them. You don't need to predict the direction, but now you need to predict what is your target, right? It could be any 64-bit value, potentially, that's in your code, that's in your code space. Well, any n-bit value where your code space, your program counter is n bits. One idea is to predict the last result target as the next fetch address. Right? Last time you executed this indirect branch, the next time you see it, use that target address. Is that a good idea? No? What if the register always stays the same? Then it's a good idea. That's right. Well, yes, usually it's not a good idea, actually. Well, it's simple, right? It's nice. You can use the BTB to store the target address on 1 bit, saying that this is on an indirect branch. And that 1 bit is needed so that you can always take the target from the BTB and not PC plus 4. Because PC plus 4 is definitely not going to work here, right? But it turns out this is actually inaccurate. Empirically, this turns out to have 50% accuracy in your prediction. Many indirect branches switch between different targets, but not all the time. So if you have a virtual function call, there's a reason why this may work, right? If you have a virtual function call and your objects are always the same, then you can get 100% accuracy, right? You guys know about virtual function calls? You can have a shape, a class, and maybe a circle and a rectangle. And you're going through a bunch of shapes and calculating their areas. Great. I don't know why you would do that, but there could be reasons to do that. You can have a while loop that goes through a bunch of shapes and calculates the area of shape, area x, I guess. Shape area. And this is a virtual function call. Depending on the type of the shape, a different function is called. Hopefully for circle versus rectangle, right? You need to calculate the area of circle differently from the area of the rectangle. If it turns out that your input set has mostly circles or mostly rectangles, then this could work, right? Last time predictor. But if it turns out that you're alternating between circles and rectangles in your input set, then you'll get 0% accuracy. So you're really at the mercy of your input set, if you will. Well, with a case statement, it becomes even more difficult potentially, right? You can do a case statement based on some text. Well, switch, I guess. With a switch case statement. You can switch based on the value of text, and you can have many cases, right? If the value is this versus this versus this. If the value is this, do this. If the value is this, do this. If the value is this, do this. And this could be an indirect branch, right? And if it turns out that your value is always the same, then the last time predictor will work. Right? Again, input set. So a better way of doing this, something that improves accuracy, is history-based target prediction. And I gave you the idea previously before. Basically, use also history information. Take the program counter of the branch, and instead of using this as your index into the VTB, also use the global history register. and then index into your BTB. Well, you can XOR it, for example. Now you have multiple different targets for a given branch in the BTB, depending on what history you saw the branch at. So if there's predictability saying that if you came to this branch, indirect branch, through this path in the control flow, normally you take this case. If you came to this branch through this path in the control flow, normally you take this other case. So if your target is dependent on which path you follow to come to the indirect branch, this gives you better accuracy. So it's more accurate. Actually, the accuracy goes up to 80% or so empirically. The downside is now your indirect branch maps to many entries in your branch target buffer. Right? For a given set size, indirect branch has many entries. Right? Even if those entries may be the same. Right? Because the branch, your input set may be such that you always execute circles. Right? So you have inefficient use of space. Okay, let's cover some more issues in branch prediction. Looks like we're not going to finish count out of order execution today. Well, we've covered this actually. So how do you identify a branch before it's fetched? So it should be clear right now, so I'm just going to skip this. So if you have a BTB hit, you know the branch type. What if you don't have a BTB? Then you have a bubble in the pipeline. Right? That's the purpose of the BTB. IBM Power 4 actually had a bubble in the pipeline. Latency, you have brought up latency. Prediction is latency critical. You need to really generate the next fetch address for the next cycle. And bigger, more complex predictors are more accurate but slower. So you have a trade-off. So we want to generate the next fetch address. It could be this. It could be the BTB target. It could be the return address stack target. It could be the indirect branch predictor target. It could be the result target from the backend. Right? So now you have a big mux. Right? And this logic could be on your critical path. Okay. So let's, actually in superscalar processors, this becomes even more complicated. Right? Now you're fetching multiple instructions. Right? You're fetching 5 instructions, let's say. And any of them can be a branch. Right? So how do you predict what is your next fetch address in that case? I'm not going to solve this problem here, but I'll just pose the problem so that maybe you can think about it. Many Intel processors today fetch 4 instructions in parallel. And you can have any of these instructions to be a branch. A branch could be here, or all of these instructions could be branches. Right? So what is your next fetch address in the next cycle? Or you could have branch, add, branch, branch. This is the first instruction. This is the last instruction. So this becomes more complicated as your width, pipeline width increases also. And here I sketch out basically a two-way superscalar processor. If both instructions are not taken control flow, then it's easy, right? Your next PC is PC plus 8. If one of the instructions are taken control flow, then you need to predict the target address for one of those instructions. The question is, how do you predict the target address? Do you index into your branch predictor 4 times? Or do you have 4 ports into your branch predictor? Right. So it becomes a little bit difficult. I'll let you think about it. And if you actually want to know more about this, you can take 740, where we go into these material in more depth. Okay, so now that we covered superscalar processors, I just wanted to add this. What is a superscalar processor? We're really doing multiple instruction fetch with superscalar processor, right? So this is the cartoon that I drew for a pipeline processor. You're fetching 1 instruction per cycle in a pipeline processor, right? Fetch, decode, execute, write back. The next instruction is fetched after the fetch of the previous instruction is complete. Now the downside is if you fetch only 1 instruction per cycle, you can only retire 1 instruction per cycle, right? You can only finish. Your throughput can be only 1 instruction per cycle. That's called the Flynn's bottleneck. So the idea of multiple instruction fetches, well, we want to make the throughput of a pipeline much larger, throughput of a machine much larger. So why don't we fetch more than one instruction per cycle? So this is an example where you fetch 4 instructions per cycle. Of course, you need to somehow replicate the pipeline in this case, right? Because you need to be able to decode, you need to be able to execute, and you need to be able to store result for 4 instructions per cycle. But this significantly improves your throughput. And this is what modern machines employ. I talked about Intel processors. They have 4 white fetch engines. So in general, n white means n white fetch means how many instructions you fetch in a given cycle. So you could do this in 2 different ways, and we briefly discussed this earlier. For a VLIW processor, very long instruction word, compiler decides what instructions should be fetched. Right? Compiler basically says, oh, these 4 instructions are independent, I'm going to bundle them, and the hardware can fetch them and execute them seamlessly. The other way of doing this is basically not having any compiler support and having superscalar execution. Well, the advantage of having the compiler deciding what can be executed in parallel is this is simple hardware, right? Because think about how you do this in hardware. For a superscalar processor, when you fetch these instructions, okay, maybe you can fetch them independently. Let's say they're all independent. They can be fetched independently. They're not branches. In the decode stage, somehow you need to figure out whether these instructions that you fetched concurrently are dependent on each other, right? What if you had a load here, writing into R1, add reading from R1, and branching based on the condition of the add, and a multiply that's also reading from R1. These instructions are all dependent on each other, right? And for the machine to execute correctly, you need to determine that dependency in the same cycle, if you will, or concurrently. Remember, in a pipeline, you're detecting dependencies on instructions that are already in the pipeline. In later stages in the pipeline. When you fetch it, when you decode an instruction, you're checking dependencies of this decoded instruction. You're asking the question, is this decoded instruction dependent on any other instruction in the pipeline? Here, you need to do that, but also you need to do, is this instruction that I'm decoding dependent on any other instruction I'm concurrently decoding at the same time? So your complexity increases. Maybe you can think of how to write the dependency check logic for the superscalar machine when you're fetching multiple instructions per cycle. Any questions? Okay, so the upside of superscalar, your throughput increases, right? You can finish multiple instructions per cycle. I'll define retire very soon. You can finish execution of multiple instructions per cycle. The downside, now you need to detect the dependencies, and you need to ensure that these instructions can execute concurrently. Your hardware becomes more complex. Other way of doing it, VLIW, now the compiler needs to figure out which instructions can be executed concurrently and pack them together. This way hardware doesn't need to figure out the dependencies. Again, simple hardware, complex compiler. Of course, if the compiler cannot figure it out, cannot find instructions, if the compiler cannot find instructions that can be executed concurrently, it'll put no ops. Right? So you're used to that solution, hopefully, by now. And there have been machines implemented with the VLIW paradigm, and they suffered from this no-op problem because the compiler couldn't find a lot of instructions to put together. I think if I remember correctly, which machine was that? I think Metaflow. There were 2 big VLIW companies in the 80s, Metaflow and Sidrome. And Metaflow had a 28 white engine, so you could fetch 28 instructions per cycle. And don't quote me on that, I think it was 28, but it was something large. And it was the compiler's job to figure out 28 instructions that are independent of each other. And it turned out this was a very difficult job. Now these companies didn't become successful, not necessarily because of technical reasons, but they were competing with some giants like Intel, for example. But they did suffer from this no-op problem, if you will. VLIW's no-op problem, which how do you fill the slots with useful instructions? Superscalar machines don't have that problem, but they have another problem. Think about designing a 28-wide superscalar engine. Your dependency check logic becomes your critical path, if you will, right? Because you need to ensure that any dependencies between those 28 instructions that you're concurrently fetching or concurrently decoding are detected and satisfied. Okay. Okay, I guess I will keep going. Because we were supposed to finish this, huh? Do you have any questions on Superscalar, VLIW? Okay, everything is clear. So one thing we have not covered so far is how does pipelining interact with sequential semantics? Remember the von Neumann model? We said an instruction is the next instruction is executed on after the previous instruction is complete. But right now we're kind of breaking that model. We're really fetching the next instruction while we're executing the previous instructions. So how do we preserve sequential semantics in this case? Well, where does sequential semantics matter in this case? You will see this in your labs. But not all instructions take the same amount of time for execution, right? This is where things really matter. So you can have multiple different functional units that take different number of cycles. That's fine. They can be pipelined or not pipelined. And you can potentially let independent instructions to start execution on a different functional unit before a previous instruction finishes execution. Right? Now this could lead to issues. For example, well, as I told you, instructions can take different number of cycles. If you look at an integer add, let's assume that it takes 1 cycle. If you look at an FP multiply, let's assume that it takes, I don't know, how many cycles is this? 8 cycles? Yeah. 8. Okay. You can still count. So let's assume that independent instructions can be sent to different functional units. Right? In this case, floating point multiply, it's sent to the functional unit at this cycle. This is time going this way. The next cycle, add is the same cycle add is decoded, and the next cycle add is sent to its functional units. And add finishes the next cycle before the floating point multiply, because floating point multiply takes a long time, right? And add writes its result to the register file. Well, this could have been a store also, right? It could write its result to memory, maybe. Well, what's the problem with this? We've broken the sequential semantics, right? We shouldn't really write to the register file right here. And there are other problems actually here. Well, if this floating point multiply actually incurs an exception somewhere, let's say you're doing some floating point multiplication or you're doing a store, and you figured out there's an exceptional condition here. If you know floating point, maybe you figure out that there's a divide by 0 over there. Maybe the result is not a number at that point because it cannot be represented with the floating point format you have. And you figure out the exception right here. Now you have an exceptional condition. You have to really back up the state of the machine, right? But you've already updated, I don't know, register 3 here and some other registers here. Right? So now you have really violated the idea of precise state. So if fmul incurs an exception right here, then you're not going to, you cannot preserve the semantics, sequential semantics of the ISA. So we need to handle this somehow. So before we part, maybe I'll just go over what is the difference between exceptions versus interrupts, and then we'll come back because that will affect how we handle things. So exceptions versus interrupts, you probably heard the terms, right? Have you heard the terms to be used the same way? An exception is the same as an interrupt? That's right, yeah. So I would like to distinguish between these two to be clear. Exception is internal to the process, whereas interrupt is external. So that's the major distinction. You will not see the same distinction everywhere, but I think to be clear in this course, I'm going to assume that exception is internal and interrupt is external. So cause is different. Exceptions internal to the running thread, interrupts external to the running thread. And this determines when they can be handled, right? If it's internal to the running thread, if that floating point multiply generating that exception, you better not execute and make the results of the next instruction visible to the architectural state, because you have a problem in that sequential program, right? Which means that you better handle this exception when you detect the exception, and then you know that this exception is real, meaning it's not on the wrong path, for example. Okay. Whereas interrupt, you can handle it when it's convenient, right? It's really external. It's something not related, if you will. It could be related, but it's something not immediately related to this particular process that's running. Okay? Except for some cases, right? Except for some high priority interrupts. For example, if someone pushed the power button, you might want to actually handle that interrupt right away. Save your state somewhere and prepare for something. Or machine check interrupt. This is a problem usually happens when the hardware detects an error, for example. If the hardware detects an error, it raises the machine check interrupt, and that is usually handled at high priority because there's something wrong with your hardware. You may not want to continue executing what you're doing, right? Okay, so the priority of an exception is usually the priority of the process. Whereas this is the system level priority, whereas the priority of the interrupt depends, really, system level priority. That's another way where exceptions are different from interrupts. Because again, exception is internal to the process, right? It's really this process that caused this exception. Okay, and handling context, again, the context is within the context of this process because the exception is part of the process, whereas interrupt is more of a system level event because it's external, right? The system needs to be involved in the handling. So I just want to clarify the differences between exceptions and interrupts because the way you handle them in a pipeline will be different. Okay, let's continue from here next time.